Hello friends, welcome to my second lecture on partially ordered sets. So, let us suppose we have two sets S and T. Okay. Let us take two elements S dash in S, T dash in T. Then we define the product set S cross T as follows. Okay. S T precedes S dash T dash if S 1 precedes S dash in the set S. So, this is the precedes notation and suffix 1 here, okay, that means for S, okay, and then T precedes T dash in T. So, that is why we have written 2 here. So, this is this notation means it is the partial order relation in T, and this is partial order relation in S, and this is partial order relation in S cross T. We shall show that this is partial order relation in S cross T. So, S T and S dash T dash belong to S cross T. So, if you take two sets S and T, then their product set S cross T is defined as S T precedes S dash T dash if S precedes S dash in S, T precedes T dash in T, where S T and S dash T dash belong to S cross T. This is called as product order. Now, let us show that if A is a partially ordered set with this notation, B is a partially ordered set with this notation, they are posets, okay, then A cross B, okay, is a poset with partial order relation defined like this. A B precedes A dash B dash if A precedes A dash in A, B precedes B dash in B. Okay. So, let us prove that this relation is a partial order in the set A cross B. So, let us first show a reflexive property. Okay. So, we have to show that A is R related to A, that is we have to show that A this and this for this, okay, A is less than precedes A in A and A precedes A in B. Okay, we know that A is reflexive. Okay, we can we have to prove this. Okay, we have to prove this that A is related to AA. Okay, in A cross B. Okay, and relation is this. That means we have to show this one. Okay, now let us notice that A is partially ordered set, B is a partially ordered set. So, when AA belongs to A cross B, then A will belong to A belong to A cross B means A belongs to A and A belongs to B, and A belongs to A and A belongs to B means A precedes A in A and A precedes A in B. Okay. Now, these two together then imply that AA precedes AA in S cross T. Okay. Now, let us say antisymmetric. So, assume that AB is related to A dash B dash and A dash B dash is related to AB in S cross T. Okay. Then we have to show that AB and A dash B dash are same. Okay. So, AB is are related to A dash B dash means what? AB is AB is related to A dash B dash means AB is precedes A dash B dash and A dash B dash is related to AB means A dash B dash precedes AB. Okay. So, by definition, okay, A precedes A dash, B precedes B dash. Okay. then A precedes A dash in S, okay, B precedes B dash in T. So, this is 1 here, this is 2 here, because in T we are taking 2. So, okay, and A dash B dash precedes A B means A dash less than precedes A in S and B dash precedes B in T. Okay. Now, let us see, A precedes S dash in S and A dash precedes A in S, together we consider. So, A precedes A dash and A dash precedes A, okay, and S is a partially ordered set. So, this implies that A equal to A dash. Next, B precedes B dash and B dash precedes B, okay, and T is a partially ordered set with the this partial order relation. So, not T, it is A and B we are taking, okay. So, S is A and so this is A and this is B, sorry, this is A, this is B, wherever S T we have written, they are actually A and B. So, so A is, this is in A and this is in B, okay. Now, what? So, B precedes B dash in B and B dash precedes B in B implies that B equal to B dash, okay. Thus, A B is equal to A dash B dash. So, that is the proof for the antisymmetric property. Now, let us go to the transitive property. Okay, so let us say A B be related to A dash B dash and A dash B dash be related to A double dash B double dash, okay. Then we have to show that A B is related to A double dash C double dash and relation R is this precedes in A cross B, okay. So, A B is related to A dash B dash means A B precedes A dash B dash, which is nothing but A precedes A dash in A, B precedes B dash in B, okay, and A dash B dash A double dash precedes A double dash B double dash, no, A dash B dash or A double dash B double dash means that A dash B dash precedes A double dash B double dash, but this means that A dash precedes A double dash and B dash precedes B double dash, okay. Now, let us consider this one and this one. So, A precedes A dash and A dash precedes A double dash implies that A precedes A double dash, okay, because A is partially ordered with this is a poset. This is a poset, okay, and B is partially precedes B dash and B dash precedes B double dash, implies that B precedes B double dash, okay, because B, this is a poset. Okay, so A precedes A double dash in A, B precedes B double dash in B. This means that AB precedes A double dash B double dash, and hence this relation is transitive in A cross B. Okay, so A cross B is a poset when A and B are posets. Now, let us see, we go to the partial order relation precedes defined on the Cartesian product A cross B is also called the product partial order, and the poset A cross B with this partial order is called as product poset of posets. A precedes 1 and B precedes 2. The same concept can be extended for any finite number of posets. If A1 is partially ordered set with this notation, A2 is partially ordered with this precedes 2, and then An with this n posets, then A1 cross A2 cross An with this notation for precedes is a poset, where this notation is defined on A1 cross A2 cross An as A1 A2 An precedes B1 B2 Bn if and only if A1 precedes B1 in A1, A2 precedes B2 in A2, and An precedes Bn in An. So, we can easily extend it. Now, suppose n cross n is given the product order, okay, n cross n is given the product order where n has the natural order, okay, less than or equal to. We have to insert the correct symbol, this symbol or this symbol, okay, between each of the following pairs of elements of n cross n. Okay. So, we have to see whether we have to put this symbol or this symbol or this symbol, whether they are now where n has the natural order. Okay. So, n with less than or equal to, okay, is a well ordered set. Okay. It is because you take any two elements, one is always less than or equal to the other. So, it is always well ordered or totally ordered with this. Now, we have to insert the correct symbol. So, 5771, you can see 5771. So, we see that 5 is less than or equal to 7, okay, but 7 is not less than or equal to 1. Okay. 7 is not less than or equal to 1, okay, and therefore, we can say that they are not comparable. Okay. They are not comparable. Now, let us look at 548. So, 5 is greater than or equal to 4, okay, and 5 here is less than or equal to 8. So, again they are not comparable. Now, 7 9, if you consider 7 is greater than 4, 9 is greater than 2. So, we can put the strictly it strictly succeeds for 1, okay. 7 9 strictly succeeds for 1. So, we have to put this notation for strictly succeeds, and then 4 6 4 2, okay. 4 less than or equal to 4, 6 less than or equal to 2. So, that is not true. So, we can say not comparable, okay. And then 1 3, 1 is less than or equal to 3, less than or equal to 7. So, we will put because 3 is less than 7. So, we can put this one here, okay. And then 7 9, 7 is less than 8, 7 is less than 8, 9 is not less than 2. So, this is not comparable. Okay. So, we can see A part, B part, D and F, they are not comparable, while C and E are comparable. In C, we have to put this strictly succeeding, and here we strictly preceding, because although 1 is equal to 1, 3 is strictly less than 7, and here 7 is strictly less than 7 is strictly greater than 4, 9 is strictly greater than 1. Okay. So, now let us go to lexicographic order. Given two posets A1 and A2, be constructed and induced are lexicographic partial order preceding L. L represents lexicographic on A1 cross A2 by defining x1 by 1 is x1 by 1 precedes in the lexicographic order x2 by 2 if and only if x1 is strictly precedes x1 strictly precedes x2, either this should hold, or if x1 is equal to x2, then by 1 precedes by 2, that should hold. Okay. So, this definition is defined recursively to Cartesian products of partially ordered sets A1 cross A2 cross An. Let us see how we do this. So, we can take an example on this. Suppose we have two sets A1 A2. Okay. Z plus means set of positive integers, okay, and the A1 is poset with this divisibility, A2 is also a poset with the divisibility. Then 2 4 is lexicographic to 2 8. How 2 4 is lexicographic order to 2 8? We can see. See, this is x 1 by 1. This is if we go by this notation. So, say this is x 1 by 1, okay, and this is x 2 by 2, then we have x 1 equal to x 2, okay, equal to 2, x 1 equal to x 2 equal to 2, and 4 divides 8, okay, this 4 divides 8. So, 4 so we have this condition holds true here, you see here x 1 equal to x 2 and by 1 is strictly by 1 precedes by 2, precedes here is divisibility. So, by 1 divides by 2, that means 4 divides 8. So, we have 2 4 is lexicographic to 8, and then 2 4 is not related to lexicographic to 2 6, because 2 is equal to 2, that is x 1 equal to x 2 equal to 2 holds, but 4 does not divide 6. Okay, 4 does not divide 6, and here in 2 4 what we see, 2 is less 2 divides 4, okay, we see that 2 divides 4, okay. So, that means that 2 4 is related to 4 in the lexicographic order. Now, let us see, because either this should hold, or if this is equal to this, then this should hold. So, here we notice that this x 1 divides x 2 holds. This notation we have defined here as the divisibility, you can see. So, here 2 divides 4, and therefore, we say that this lexicographic partial order holds for between 2 4 and 4 5. Okay. Now, let us take this one, A I equal to z plus, set of positive integers, okay, and all these A I's, okay, are posets with this divisibility order, okay, divisibility they are posets with divisibility. For this is valid for I equal to 1 2 3 4, all of them, okay. Then let us look at this whether this is related to this under this lexicographic order. So, you see 2 is equal to 2, okay, 2 is equal to 2, then 3 divides 3, 4 divides 8, but 5 does not divide 2, okay, and therefore, this is not related under this order, because we notice that when x 1 is equal to x 2, then by 1 should divide by 2, by 3 should, I mean this is, suppose this is x 1 by 1 x z, I mean let me call it as x 1 x 2 x 3 x 4, okay, and this one we call as by 1 by 2 by 3 by 4, okay. So, we notice that x 1 is equal to by 1, okay, x 1 is equal to by 1, then x 2 should divide by 2, x 3 should divide by 3, x 4 should divide by 4, which is not true because 5 does not divide 2. Now, here 2, 3, 4, 5 let us take, and 3, 6, 8 here. So, then 2 is 2 does not divide 3, okay? 2 does not divide 3 and 2 is also not equal to 3. So, this is not related under this relation. Now, 2, 3, 4, 5, 2, 3, 5, 10. Okay. So, here 2 is equal to 2. Okay. Now, 3 divides 3, 4 does not divide 5. Okay. 4 does not divide 5. So, this is not related under this relation to this 2, 3, 5, 10. Immediate predecessor and immediate successor. Let S be a partially ordered set. Okay. S be a partially ordered set. Say I can take the partial ordering to be this. Let S be a partially ordered set. Okay. On S, this is the partial order. Okay. Precedes. We say that A is immediate predecessor of B in S, or B is an immediate successor of A in S, written like this. Okay. A is immediate predecessor of B. If we want to write that, then we put this symbol. Okay. So, A is immediate predecessor of B, or B is immediate successor of A. Okay. If A is less than B, but no element of S lies between A and B, that is, there exists no element C in between in S such that A is less than C less than B, and C is related to A and B by this partial order. Okay, that we have to see. Now, let us see this example 2, 3, 4, 5, let us say S is equal to 2, 3, 4, 5, 12, 16, 24, 36, 48. Let us say it is this set is partial poset with respect to the divisibility. Then we have to find predecessors and immediate predecessors of 12. Okay. Now, so predecessors of, when we want to find predecessors of 12, we should find the elements which divide 12, okay, and which are less than 12. So, 2, 4 divide 12, okay, are predecessors of 2 and 4 are predecessors of 12. Now, 2 is not immediate predecessor of 12, because 2 divides 4, 4 divides 12. So, there is 4 in between 2 and 12. Okay. Because of the occurrence of 4, and 4 is an element of S. So, because of this 4 which occurs between 2 and 12, okay, this 2 is not immediate predecessor of 12. Now, let us see whether 4 is immediate predecessor of 12 or not. 4 is, of course, 4 is an immediate predecessor of 12, because there is no element in between 4 and 12, okay, which is say you can say that that element is C such that divides 12. Okay. So, there is no, since there is does not occur since there is no element C in between 4 and 12 such that 4 divides C and C divides 12, okay, C belonging to S, okay, and therefore, 4 is an immediate predecessor of 12. Now, let us look at the successors and immediate successors of 12. So, 24, 36, 48, okay, because 12 does not divide 16. Okay. So, successors of 12 are 24, 36, 48. Okay. So, successors of 12 are 24, 24, 36, 48. Now, we have to see we have to find immediate successor of 12. Okay. So, immediate successor of 12 immediate successors of 12 are 24 and 36, because between 12 and 24 16 is there, okay, and 16 12 does not divide 16, okay. So, 16 does not divide 24. So, there is no element between 12 and 24, okay. Therefore, which is divisible by 12 and which divides 24. So, we say that 12 is an 24 is an immediate successor of 12. Also 36 is an immediate successor of 12, because what do we notice that 24, although 24 lies between 12 and 36, but 24 does not divide 36. Okay. So, 36 is also an immediate successor of your 12. Now, we go to representation and Hasse diagrams. A partial order precedes on a set X can be represented by means of a diagram known as Hasse diagram of X in poset X. Now, in such a diagram we represent each element by a small circle or by a dot, and any two comparable elements. Comparable elements, let us see, two elements of a poset are called comparable if A precedes B or B precedes A is true. Okay. So, any two comparable elements are joined by lines in such a way that if A precedes B, then A lies below B in the diagram. Okay. Now, non-comparable elements, if there are two elements which are not comparable, that is A does not precede B and B does not precede A, then such elements are not joined. Okay. So, we have to remember this. Now, thus there will not be any horizontal lines in the diagram of a poset. If Hasse diagram of a poset is given, then we can obtain the set of ordered pairs in this notation from the diagram. We can write the ordered set of ordered pairs from the Hasse diagram. Now, a Hasse diagram for a total order relation. Okay. If your relation on the set X is a total order relation, total order relation means if you take any two elements of the set X, then they are comparable, either X is precedes by or by precedes X. So, then in the Hasse diagram what we will get is a single vertical chain. Now, let us see how we consider how we draw the Hasse diagram in some examples. Let X be equal to 2, 3, 6, 12, 24, 36, and the relation in X is such that X precedes by if X divides by. So, in the set X the partial order is the divisibility. Okay. So, X precedes by if and only if X divides by, that is the definition. Now, let us draw the Hasse diagram of X. Okay. So, let us see, we have the Hasse diagram of X here. You can see we have the elements as 2, 3, 6, 12, 24, 36, 2, 3, 6, 12, 24, 36. Okay. So, this is my set X, and we are taking the relation to be divisibility. Okay. Now, we can see X, if the element, let us say take 2, okay. 2 does not divide 3, okay. 2 does not divide 3 and 3 does not divide 2. So, between 2 and 3, okay, as we have seen earlier, we have seen that non-comparable elements are not joined. Okay. So, the element 2 and 3 are not joined. Okay. Now, 2 divides 6. So, we join 2 to 6 by this horizontal line. Okay. We join them 2 to 6, and then 3 divides 6. So, we join 3 to 6, and then 6 divides 12. Okay. So, we draw this horizontal line. Now, one more thing you remember, we have said that two comparable elements. Okay, let us see this one. Two comparable elements are joined by lines in such a way that if A, now this notation we are taking as divides. If A divides B, then A lies below B in the diagram. Okay. So, let us keep that into mind. Okay. So, this 3 divides 6 means 3 should lie below 6. Okay. So, see 6 is up here, then 6 divides 12. Okay. So, 6 lies below 12 and then 12 divides 24 and 12 divides 36. So, this is Hesse diagram of the set poset X. Now, let us take example 2, X equal to 1 2 3, then power set of X is consisting of sets phi singleton set 1 2 3 1 2 1 3 2 3 1 2 3 and the relation is inclusion relation. Okay. On the set P x, let us draw the Hesse diagram for this. Okay. So, we begin with phi. Okay. Now, phi is contained in singleton set 1. Okay. Phi is contained in singleton set 1, phi is contained in singleton set 2, phi is contained in singleton set 3. Okay. So, we join them by lines and then 1 is contained in 1 2. Okay. 1 is contained in 1 2. So, we join it by this line and 1 is contained in 1 3. So, we join by this line, this one, okay, this one, and then 3 is contained in 1 3. So, we join it by this line. Okay. Now, 2 is contained in 2 3. So, we join by this line and 2 is contained in 1 2. So, we join by this line. Now, 2 is a subset of 1 2. So, 2 lies below 1 2. Okay. 1 is a subset of 1 3. So, 1 lies below 1 3, 3 is a subset of 1 3. So, 3 lies below 1 3 and then 1 2, 1 3 and 2 3, each one of them is a subset of 1 2 3. So, we join them by these lines and then this is what is the Hesse diagram for the example 2. Okay, now, let us go to the third one. Let X be the set of factors of 12 and let this be the relation divides, that is X precedes by if and only if X divides y. So, we take the division relation. Let us draw the Hesse diagram of this. Okay. So, we have 12, the factors of 12 are 1 2 3 4 6 12. Okay. 1 2 3 4 6 12. Now, we begin with 1. Okay. So, 1 divides 2. Okay. So, we join 1 to 2, 1 divides 3. So, we join 1 to 3. Okay. Then 2 divides 4. So, we join 2 to 4. Okay. And 3 divides 6. So, we join 3 to 6 and 2 also divides 6. So, we join 2 to 6 and then 4 divides 12, 6 divides 12. So, we join 4 to 12 and 6 to 12. So, this is the Hesse diagram for the third example. So, with that I would like to end my lecture. Thank you very much for your attention.